So we are just waiting maybe 1 more minute to start. Yeah, so let's wait a little bit, few more seconds for more people. We have about 76 people I see joined. So yeah, so maybe I get started. I'm gonna share a short presentation with you guys. And yes, okay, so just a second and beginning. Okay, so hello and good afternoon, everybody. This is the CMCC CDR webinar series, monthly webinar series. We are very happy to have you all here with us. I see that about 100 people are joining us, very good number. This webinar series, as you know, it happens every second Wednesday of the month at 2 p.m. Central European Time. You need to register to attend these webinars. So there will be a link that you already have received. Just follow up with that link and also with the emails that you receive through different channels. We are trying to disseminate this event as much as possible. And it is gonna cover different papers that are coming out of the UPTAKE project. I'm gonna talk about the UPTAKE project in a little while, but this webinar series is dedicated to presentation of the papers which are supported in the UPTAKE project. So a little bit about CMCC, who we are, and organizing this webinar series. We are a leading research institute in Italy. We have 3 main research institutes in different cities in Italy. We are presenting all the research is focused on climate change research. We also have 3 programs, cross-cutting programs. The one that hosting this webinar is integration of the planetary and industrial carbon cycle, the one that I am the director of the program. A little bit about other parts of CMCC. We also have centers, 3 centers. One of the centers at CMCC is Advanced Training and Education Center, and it aims to basically train young researcher, PhD student, postdocs, and young researcher about topics related to sustainability and climate change. It collaborates with researchers internationally and share the experiences through these activities that they do at this center. One of their main activities, organizing the summer schools and different short courses schools. So you can see here the past schools that the center has organized. And I want to use this opportunity to let you know about the upcoming summer school that we will have dedicated to CDR. So carbon dioxide removal for a net zero future. It's going to happen at the beginning of June this year for 2 weeks. And we are very happy to have also Felix, who is the presenter today. He will be one of the instructor in the course, and I will be there also as an organizer of the summer school. More information and how you can apply and register for the course, you can scan the QR code or go to the webpage and learn more about this course. A few words about the UPTAKE project. It's a Horizon Europe project funded by European Commission. About 20 partners across Europe are collaborating on different technologies, CDR technologies and methods, and looking at ways to upscale these technologies. The project started in 2023. It will go through 2027, and the total budget is 7 million. We have developed a platform which allows the members of the consortium and also outside the stakeholders to interact with each other. Again, there is another QR code for you if you would like to scan and join this platform. This is a very good way to learn more about the project and see the latest updates of the project. We also try to share broader news and publications which are coming out of other project and research groups. So it's a very nice way of interacting with people in the community. Finally, the webinar today is going to be about the durability of carbon dioxide removals. So we are presenting two papers, and we have a moderator, Pavel, and the panelist, Robert, who will talk about different aspects of CDR, especially in terms of durability. Having said that, I would like to just remind you, if you have questions, please use the Q&A option at the bottom of your page. You can post the question, you can interact with the speakers and other participants in the webinar. And stay tuned for the next webinar that we will have on April 9th at 2 p.m. CET. Having said that, I will leave it to Pavel to moderate the session. Thank you very much.
Thank you, and I won't be long. My name is Paweł Wiejski. I'm from the Reform Institute in Warsaw. We're also part of the Horizon project, and we have two presentations today, and then we're going to have a panel discussion. First up, I would like to invite Cyril Brunner from Zurich to give the presentation, and the floor is yours.
Great. Thank you very much for having me. I have the pleasure of introducing you to something that I was looking into with my colleagues Reto and Sieg. That is about the durability of carbon dioxide removal. Now, I think we are all very well aware what carbon dioxide removal is and what isn't carbon dioxide removal, and definitions like the one here from the IPCC is helping us to align all of that. So the definition by the IPCC is that it is anthropogenic activities that remove CO2 from the atmosphere and durably store it in geological, terrestrial, or ocean reservoirs. Okay, so far so good. There's several interesting bits about that within that. First of all, it needs to remove CO2 from the atmosphere, so any delayed emission or avoided emissions aren't considered to be carbon dioxide removal. And then it needs to be anthropogenic activities, which, if you look into national greenhouse gas inventories, how they collect the emissions and make the registers, that is actually ever so slightly different from the methodology that the IPCC is using. There's a very lovely paper by Miles Allen and colleagues that discuss that and the implications of that. And then lastly, there is also that it needs to be durably stored. But having said that, if you then dive into the literature, the scientific literature, then you find out that actually there hasn't been much work on that, at least prior to our paper. Some work look into sort of what is the effect of temporary removals, but not too much detail on what is then durably actually corresponding to. And that is a challenge, since now many policies are currently being drafted around the concept of carbon dioxide removal. And then policymakers need to define what actually, or decision makers and policymakers need to define what actually carbon dioxide removal is and what isn't it. And there they also need to define what durable corresponds to. And this ranges from, say, decades up to centuries to millennia or so. And so what we wanted to do with our manuscript is to clarify this point here, and to shed some light on the implications that it has on the climate effect if you use different definitions of durability. Starting with that, a lot of people that I hear also within the climate science community, they always think about the concept of how long CO2 stays in the atmosphere. And I think it's really important to make this distinction between how long CO2 stays in the atmosphere and how long it warms actually in the atmosphere, because the two are not the same. And I have here a small example of that, a scenario where we have a single emission of CO2, 1,000 gigatons, and then we look sort of how long does the CO2 stay in the atmosphere, and if we take some period, say 100 years, then what we see is that roughly a third of that CO2 is still in the atmosphere after 100 years. However, if you look at the warming, induced warming from that, then we see that actually still 90% of the warming persists after 100 years. So now you can already tell that it makes a huge difference whether you talk about how long CO2 stays in the atmosphere or how long it warms in the atmosphere. And I think our challenge is the latter, not the former, in that respect. that being said, I would like to invite you to a thought experiment where we dive into sort of initially a very similar experiment that we had before, where we have a single emission of CO2. This time it's 1,000 times less. And then we look at the warming that it causes over the course of time. And what we see is that the induced warming persists for millennia to come. Now, at the same time, we can also make a thought experiment. What happens if you remove a gigaton of CO2 from the atmosphere and just look at the implications that this single removal has on the climate? And what you can see is that it actually induces a cooling that also persists for millennia to come if this removed CO2 stays removed. And now what we also can do is we can combine the two. You can have simultaneously a removal and an emission. And this is what we call a net zero emission. And then what we see is that the net effect is actually that this doesn't cause any warming. And it also makes sense conceptually, because if you simultaneously emit a ton and remove a ton, then the net effect is going to be zero, at least in a simplified manner when you don't globally resolve this. However, that being said, now, if you think about the different methods of how we can actually remove CO2 from the atmosphere as a society, and here I show you an overview from Carbon Gap, but there's many others around, and I find this just illustrating, then we see that these don't store CO2 forever. Some of these methods, they store CO2 actually for decades, some for centuries, some for millennia, and then some even longer. And so in reality, I think there is implications of doing carbon dioxide removal with a limited duration of how long you can store it. And the question is, where do we make the cut? Where do we define this is now durable and this isn't durable? aka, this is considered to be carbon dioxide removal and this isn't. Now, to model that, you also need to model how the CO2 gets re-emitted into the atmosphere. And I would say there are three main kinds of how this can happen. The first one, and I illustrate this here with showing you the net emissions over the course of time. And pay attention, I needed to cut here the axis, otherwise sort of this line would go all the way here to the bottom and all the way to the top. So the first way of what we can think about of how CO2 gets removed and then re-released is sort of you have a removal, say, of 1 gigaton of CO2 in the 0 year, in the initial year, and then after a time period, which you call a durability or permanence of this carbon dioxide removal method, you have a re-release of the full removed part. So if we look at the cumulative emissions, basically the CO2 remains removed until you actually pass this durability, and then all at once gets re-released into the atmosphere. So that is one possibility, and you can think about if you build a house or so with fast-growing biomass, and then you deconstruct the house and you burn all the biomass, that could correspond to such a scenario. What also could be is sort of that you remove a gigaton of CO2, but then continuously over this durability have a constant re-release. And with that, the cumulative emissions is also equally high initially, but then gradually declines until approaching zero by the end of what you call durability. However, when you think about the different methods of how we can remove CO2 in the atmosphere, a lot of the re-release is basically is due to a chemical reaction or to a leak or some sort of that. And the behavior of that is often like that you remove the CO2, and then over the course of time, you have a re-release that is higher initially, but decays over time. And we call that lifetime re-release because it's very similar to the lifetime of atmospheric gases and how they're being called in that sense. Now, when we did our manuscript, we were focusing on this part, on the lifetime re-release. However, we also provide the other re-release methods or approaches that I showed you before in the supplement. Okay, now if we go back to our thought experiment where you say you have a CO2 emission and then you make a net zero claim by also simultaneously remove CO2 from the atmosphere, but now this CO2 doesn't get stored permanently, but only for a defined amount of time, then you can think about the upper limit of what we can define durability as 0 years. So right away, right after removing it, you would have a re-release. Not that I'm advocating for that, but I just want to show you sort of the upper bound of a possible definition. And obviously, if we had the direct re-release of the CO2 that we removed, so say if breathing would be considered carbon dioxide removal, we inhale, we remove some CO2 from the atmosphere, but we don't store it for very long and exhale it right away, then the induced cooling of that would be somewhat negligible. And the net effect would be actually the same as if we hadn't done any carbon dioxide removal in the first place. Then we can also think about how this would look like if you removed CO2 and stored it for 100 years. And again, here you have initially quite a lot of induced cooling that is able to fully balance the CO2 emission, but with time you lose the CO2 that you removed, and you actually get back to the same level of warming that you had if you hadn't done any carbon dioxide removal in the first place. So that corresponds to a net zero claim with a definition of durability of 100 years in that sense. And then the same is for 1,000 years. It looks different. And then in our manuscript, we actually provide an overview with these different re-releases after following a pulse emission and the claim of net zero emission. Now, in reality, we not only emit one single pulse of CO2 that we would like to balance with carbon dioxide removal, but actually we have continuous emissions currently, very small amounts of carbon dioxide removal, and then we want to reduce our emissions to net zero emissions, where we will still have some residual CO emissions, which we want to balance via means of carbon dioxide removal to net zero. And this is what we show here. So here we have a scenario where we do have the present day emissions, which we reduce the CO2 emissions to net zero by 2050. The other non-CO2 emissions, including the aerosol emissions, we kept constant here. And then we maintain net zero emissions here. And we assume here residual emissions in the order of 6 gigatons of CO2. And what we can see is sort of that with permanent removal, we actually achieve the targeted climate neutral case. And if we have non-permanent CO2 carbon dioxide removal, then we see that we still have some induced warming with it that gets closer to a direct re-release. Here, the shorter this is. Now, what we looked into, what I don't show here, is sort of in addition to permanently removing CO2 from the atmosphere, what you also could do is, as soon as you have a re-release, you can do new carbon dioxide removal to replace that, and you have the same temperature outcome. So to conclude here, only permanent carbon dioxide removal or this replacement with new CDR after following a release shows the same temperature outcome during net zero CO2 emissions as if we had zero CO2 emissions. Now, this is a different scenario than what we showed in the manuscript, but you find the emissions here, and I found that more intuitive now for this case. As said, this all very much depends on the amount of residual emissions under net zero emissions, and there is a lot of debate about this, how big this is going to be. Again, here we assume 6 gigatons, which is sort of in line with most scenarios that limit warming close to 1.5 degrees. However, we also provide this overview here where we basically quantify the amount of warming per gigaton of residual emissions. And the tendency is sort of the same. Okay, does that now mean that any temporary removal is actually not really beneficial or useless in that sense? And we would argue quite the contrary. And for that, we also point to work that has been done by others, for instance, Matthews and colleagues, which, for instance, what they do is, what they show here is with this 1.6 degrees scenario, which uses permanent removals, first to get to net zero, but then also to achieve net negative emissions. And now what we see within this scenario, without any temporary removals is so that it peaks around by this time period here around 2040. Then you have, after this peak, a decline in temperature, and this is mainly due to that they reduce their methane emissions substantially, and then you have this prolonged reduction in temperature, and this is due to the net negative emissions. Now, what happens if, in addition to these permanent removals, you also had some temporary removals? This is what they looked into, and they said, okay, let's say some temporary removals prior to net zero, which you then lose gradually after net zero. And what you can achieve is that with that, you overall have less CO2 in the atmosphere, aka less warming, and therefore you reduce your peak warming. But as soon as you lose your temporary removals, the storage, the removed CO2 gets re-released into the atmosphere. You basically get back to the same trajectory that you had if you hadn't done any carbon dioxide or any temporary carbon dioxide removal. Obviously, if you were to maintain your removal, then it would follow these pathways. Now, I think as a concept, when we think about the durability of carbon dioxide removal, this is fairly new to us and we're not quite used to it, but I would argue that other concepts in our society are actually also building on the very same challenges, and we have found solutions to it. And I make this example here from the financial industry, where you could think about the expenses that you have in a financial system, sort of similar to being emissions that we have. And then in order to balance your expenses, when you want to maintain your bank account level or so, you need to get some inflow of money. And there we differentiate between money that you get and you may keep unless you spend it, that is income, we call it income, and money that you get, but after a certain time you need to give back, and we call that loan. So there, it's really important that we have this distinction, because if you just for a moment think about a society, a world in which we hadn't this distinction, I think where we wouldn't differentiate between income and loan, and basically whatever money you get, you may keep, I think the whole financial system wouldn't work as it does today. So for that reason, I would also think it's really important to make this distinction. Both are useful, temporary carbon dioxide removal, temporary removals, permanent carbon dioxide removal. I put permanent here in brackets up to a certain point, because the definition of carbon dioxide removal already says it needs to be durable. But this is certainly something we need to discuss as a society and a community. So to conclude, at the moment, there is an ambiguity around the definition of what durable storage corresponds to within carbon dioxide removal, and that puts some threat to a robust net zero framework and the implications that it has, aka to limiting warming to agreed levels, for instance, in the Paris Agreement. And we argue within our findings that a storage duration of fewer than 1,000 years is insufficient to target this climate neutral case under net zero CO2 emissions, because it still leads to continuous warming. That being said, it doesn't mean that lower durability removals are useless. They are valuable too, if they're done either in addition to permanent removals or when replacing any re-release of temporary removals with additional new CDR. Thank you.
Thank you very much for your presentation. Let me just clarify one technical thing. If you want to ask questions, please do so using the Q&A box. We cannot give you the floor, unfortunately, if you're a participant, but please do write in the questions. I will read them out for our panelists after the presentation. And moving on to the second presentation of the day, Felix Schenuit, if I remember correctly, and Josh Burke will present another paper which is very closely related to what we've been talking about and showing some practical considerations of the durability issue. So take it away.
Okay, thanks very much. I'm going to kick off with the first 5 or 6 slides, and then Felix will take over. So this is the academic output from some work we started in 2023. And the starting point for that was I was on secondment to the UK government And this doesn't represent the government's views in any ways, it's certainly my views, but whilst in government there was a big question about which type of carbon removal technology should be integrated into the UK ETS, and given the challenges presented by different technologies, how can we manage the different characteristics? So that's kind of the starting point for this research. Next slide, please, Felix. Yeah, so as I say, the motivation. So as Cyril very well set out, the CDR methods have very different characteristics, both in terms of their technological maturity, their cost, and critically for this topic, how long they store carbon for. And with that, they have very different risk profiles in terms of how likely that carbon is to be re-emitted back into the atmosphere. And this has big implications for the policy design and the governance of these methods. And it's really helpful to have Cyril's work, which we didn't have at the time, which would have been a very useful empirical starting point for this, but this work very nicely follows his. So this is particularly important for the integration of CDR into compliance markets. In the UK, we're perhaps moving at a quicker speed than the EU. There's been a good indication that BECS and DACs will be integrated into the UK ETS. There remains an open question about whether less permanent methods should be integrated, and if they do, how do we practically go about doing that? So that was the exam question here. If governments are thinking about integrating non-permanent CO2 or lower durability carbon removals, is there a way of practically creating some kind of equivalence for these methods? And that is a precondition for integration, as you need to create some kind of fungibility between different types of carbon removals. You have to kind of artificially construct some equivalence. So that was the starting point. And we decided to map out various ideas that have proliferated in the literature over the last couple of years. There's lots of new ideas, new concepts about how we manage this. So we wanted to map them and then tease out the nuances between them as they actually deal with different types of risk. Next slide, please. Yeah, so we had a version of this previously. So this just gives you an overview of how long different methods store carbon dioxide for. It's a very rapidly evolving space, I would say. So here we have things like biochar, which in the first IPCC classification, which informed this research, it was classed as having decades to century storage timescale. In this work in the State of CDR report, it then uprates that to a longest storage period. So we're in a very dynamic space. As new evidence emerges, different classifications of technologies will become apparent. So it's also worth bearing that in mind when we think about the framework we present later on. So next slide, please. Okay, so as I said, we set about trying to map the various measures to address permanence. And as Cyril mentioned, durability and permanence are often used interchangeably. And I think for the purposes of this, we're probably talking about the same thing, although there's often the nomenclature is often applied inconsistently. So the first sets of measures we identified were around MRV. So that's monitoring, reporting, and verification. And that gives you confidence that net removals have happened. And it's the basis for integrating carbon removal into policy frameworks, as it creates a tangible commodity that you can sell these credits for, either in carbon markets or the voluntary markets, for example. The second risk management set of measures we identified were around what we call liability measures, and these mechanisms stipulate a storage duration. At the end of a storage duration period, actors are continually obliged to remove carbon removal in perpetuity. And this kind of comes to Cyril's point about if we can continue this, if after the event of a reversal, if there is a mechanism that companies have to then, in real time, continue to remove carbon in perpetuity, that can mitigate that reversal event or that the end of that lifetime of a project. So this is how you might operationalize that in practice. So there might be a legal obligation for a company to remove in perpetuity. The challenge with that is it relies on the institutions and the governance frameworks to be salient and be fit for purpose in timescales that we've not really used to before. So how do we know whether the regulators will be fit for purpose in 100 years' time? We just don't know. The second is, do we know whether the companies are going to be solvent in 100 years' time, or whether they can even afford to continue a project at the end, particularly if the cost curves for certain removals go up over time, that debt, if you like, becomes more expensive. So there's big question marks there. The second set of measures that have been taken, that we mapped and have been inspired from the financial markets, are what we call de-risking measures. These are products like financial carbon insurance, which can underpin the liability, or market discount rates, for example. The fourth set of measures are durability measures. So in here, we're predominantly talking about buffer pools, really. So companies or projects can set aside a portion of their credits to sit in a buffer pool that can be drawn from in the event of a reversal. And then the last measure is what we call fungibility measures, and that is an attempt to quantitatively value CDR with different levels of permanence, and the output from this is what we call an equivalence ratio. So here's an arbitrary example, is that you can use essentially an economic approach that says 3 temporary credits are equal to 1 permanent DAC credit. That's an arbitrary example, but it gives you this kind of exchange rate mechanism that policymakers can use to create this fungibility. Next slide, please. Okay, so once we have mapped those out, the next thing to do was to demonstrate how these can be bundled together. And the idea here is that nothing is, as new evidence emerges, things change. These ideas are meant to be quite flexible, but this is just illustrative at this point. So on the right-hand side, we have the most permanent CDR, and conceptually, the idea is that the regulatory burden or the regulatory architecture that sits around it should instinctively be lower. It's more additional, it's more expensive, and it's permanent, so we don't want to overly regulate these entities so that they don't become viable. What we see across all types of carbon removal, regardless of how long they store carbon for, are certain measures that we think should be in operation regardless. So the first is MRV. You have to have that regardless of how long a method stores carbon for. The second is a liability measure. So in the event of reversal, there's a legal obligation for companies to remedy this. Those two types of measures we think are applicable throughout. The other types of measures are essentially a political choice about how heavy the government wants to regulate these things. But in essence, the more permanent, the lower the regulatory burden, the less permanent, the higher regulatory burden. Okay, next slide, please. So this is where it would have been quite helpful to have Cyril's paper at the time. So this is how we are starting to conceptualize the different types of CDR in terms of fungibility. So we've sketched together this kind of conceptual framework, and where we outline the concepts of inter and intra-fungibility. So the idea here was to categorize CDR methods based on how long they store carbon for. On the left-hand side, we have the IPCC classifications of decades to century, where you have biochar, afforestation, soil carbon sequestration, for example. But as I said earlier, new evidence merges. These types of methods can move between the different buckets. As we've seen with biochar, that's now maybe moved one step to the right. And the idea of grouping these together is that you can then potentially create what we call intra-fungibility, where these methods are fungible and equivalent with each other. They both store carbon, they all store carbon for similar amounts of time. Critically, they're not fungible with other methods that store carbon for much longer periods, and they're not then fungible with allowances in compliance markets, which represent fossil emission. And so what we want the application of this to be is, if you can group certain types of methods together, you can then start thinking about devising policy frameworks to incentivize them. As Cyril said, we absolutely do need, and there is a lot of value in less permanent CDR. So how do we go about incentivizing that? So we could perhaps have a separate carbon market for CDR that's stores carbon for decades to century, and they could be a land use emissions trading scheme, for example, where short-lived CDR offsets shorter-lived land-based emissions. And then as we move to the right, we have at the very end 10,000 years or more, and CO2 CDR, and because what a compliance market is representing fossil emissions, you need to have something that is physically equivalent. And as Cyril said, only permanent CDR really can neutralize a fossil emission. So we then outline the concept here of intrafungibility, where these CDR methods can be laterally moved. So in the short term, because of the higher MRV maturity and higher technological readiness, BECCS and DACs have short-run interfungibility. So interfungibility where they can be fungible with carbon market allowances. And in the long term, as enhanced weathering and ocean alkalinity, for example, as the MRV frameworks become more sophisticated, they could also potentially become integrated into compliance markets. And as we'll see, BECCS and DACs, that's where the kind of political momentum is for integrating CDR methods to compliance markets. Next slide, please. And I think that's me. So I'll pass over to Felix now.
Thank you, Josh. I will do the final stretch now to think a little bit about how this is relevant for CDR policy, how this can be operationalized. And what we had in our report and the paper was that we proposed a sequencing strategy to integrate CDR into compliance markets, or groups of CDR methods into compliance markets. Why a sequencing strategy? One is because we need sufficient time for capacity building for MRV, but also, of course, for further developing the methods. Also, we will need time to establish non-market-based policies to lower the cost of permanent CDR. We all know that even if we would integrate permanent CDR into emission trading systems today, the cost for it would be much higher than price for allowances is. So we will need something in between there. And of course, the sequencing strategy also, because the signaling that it will eventually be integrated into the ETS is important as a signal that we will have this long-term demand for CDR. The sequencing strategy has basically 3 stages. As Josh already mentioned, in the first stage, we will definitely need to make sure that we have MRV systems up and running, that we have robust certification of carbon dioxide removal. This is really essential for creating trust on carbon dioxide removal and for integrating it into policy instruments, not only emission trading system, but also others. In the second stage, we really need to deal with governing risks and of reversal. So these are the de-risking, durability, and liability measures that Josh presented. And this is also then the phase where we should talk about non-market-based policy instruments, so fiscal incentives, public procurement, to really get things going on short-term demand for carbon dioxide removal, demand that we can't really provide through an ETS integration, which will take time. And then in the third stage, it is about creating tradability. So here we really need a policy bundle that combines all of the measures that we presented here. And here it is about the integration into emission trading systems. And then the question is, of course, where are we currently when it comes to the integration? Just very briefly, a few comments on the UK and the European Union. Josh already mentioned that the UK is a few steps ahead. The consultation closed, and we are maybe a little bit closer to already integrating at least BECCS and DACs there. And the government has outlined important design preferences already. I think one issue that we should talk more about is about linking ETS between the European Union and the UK. I'll come to that in a second, but I think CDR integration shouldn't make the linking more difficult in the future. In the European Union, I think most of you know that we will see a report in 2026, and when we do the revision of the ETS anyway, but not only the ETS, but also all other pillars of CDR, climate policy. And then the Commission will present its view on what could be the next steps in ETS integration. But this also shows that it will take time until we actually get the integration done. I also want to say that we shouldn't take the ETS integration for granted. It's one of the main talking points in our little CDR bubble, but my take is that it's still very early and we have many other decisions to take on CDR, the 2040 target, the LULUCF regulation, possible integration of agriculture, the effort sharing regulation. These are all questions that we should also work on. So it's not only about the ETS and the new focus on competitiveness in the European Union, but also in many member states, of course, doesn't make it easier to make the case for CDR. I want to end, or we want to close by raising 4 recommendations, also to instigate the discussion a bit, of course. The first point, we should really think about it as a sequence. So it's not about deciding all details of how we govern permanence or durability of CDR today, but we should really agree that we do the MRV and certification first, then the reversal risk, and then only then after that creating tradability. We shouldn't complicate future linking of ETS systems. So there is a risk that in one ETS, for example, we decide to include also less permanent CDR, and this would make it very difficult to link ETS in the future. So I think we should really at least discuss this dimension of it. And we should, and this is more general point, transparent about the objective of integrating CDR into the ETS. Is it about liquidity for the market, or is it about something to incentivize CDR? I think we should really be careful that CDR is not just a proxy for creating liquidity in the ETS systems, because this is a risk for CDR and creating credible incentives, I think. And just want to repeat again, we should broaden the debate. It is not only about ETS. It is, of course, the key policy instrument, both in the UK and Europe also. But there are many other decisions that we should also talk about, and where the permanence issue is also relevant. So it's not only relevant when we talk about tradability, but also in the steps before. And as we said, MRV really is the key issue that we should solve first. And with that, I'd like to thank you, and looking forward to the discussion.
Thank you so much for the presentation. And now we'll move to the debate. There are already a few questions, and we don't have a lot of time, but I would like to start by giving the floor to Robert, who is, among other things, a co-founder of CDR.fyi website. And I have 2 questions for you. One of them is for the database. One of them is for like referring to the issue at hand, which is like you deal with the CDR technologies today, and what role do the issues of permanence and durability play in getting the private financing for the different CDR methods? And the other kind of more specific question from the audience is about data on how long CO2 can be stored within concrete or other products. So are there like technologies that you know of in terms of embedding carbon in products that can store CO2 for millennia? So,
well, the first question is easy. Like if CO2 is in concrete, it's extremely unlikely that it would ever be released to the atmosphere. You need to heat it up to 900 degrees, so you can essentially see it as permanent. On the first question, so CDR.fyi, we only track durable carbon removal. We didn't want to use the word permanent because there's some, like the meaning of that as Cyril was talking about. But biochar and biomass storage, direct air capture, and rock weathering and so on, right? And that's a nascent market. It's smaller than the total removal market, including forestation, but mostly in tons or in credits. If you look at the total value of the market, then the durable carbon removal market may actually start to overtake the forest side, because the price per ton is much higher. So still, we only have a small number of companies that have engaged in this durable carbon removal market. So it's still not a strong consensus, I would say, that you would need permanent carbon removal to offset your fossil emissions. Like we're pushing for it on our side as well. And Cyril and academics are doing it. And then the SBTi also said that it's permanent carbon removal that is supposed to be used, but everyone doesn't have an SBTi target. So I would say there is a little bit of bifurcation in the market. And we did a market survey just last week together with Silvera, which is also like a rating agency for credits. So they do forests as well. And kind of from the responses, we could clearly see that at least the buyers that were responding to this market saver, they were planning to buy forest credits as well and durable. So we need to fight a bit more. And I think what people often confuse is the question of like what you need to do if you're going to continue to emit fossil fuels. Like, well, then you need permanent carbon removal. And when you put it that way, people often agree. But I think what people think about is like they see compensation as more like paying a tax or something, and then it doesn't matter that much what it's going to. If it's something that if it's emissions that you're trying to push down to zero, maybe you don't have any control over them, and you're just paying a tax to be good, then I understand why people kind of have a wider lens of this, where they would think it's fine to support forest projects or other climate projects. But if you frame it as more like as in the ETS, it's continuous fossil fuel emissions. It's something that you choose carbon removal as the mitigation option. When you do that, I think it becomes clear. But people don't really get that because they're used to compensation being a second best, like something you just put on top, like it's not an actual mitigation option. And that's why I think it's been hard to get people to understand that the permanent removal is necessary.
Right, and that brings me to another question from the audience that deals with as I understand it was pretty long, but it deals with the issue of the overshoot, right? So like that in the future there will be a need to reduce the temperature of the Earth and not only to get to net zero. So do you think that like what role do the permanent CR play with this?
That's a great question. I was a co-author on another paper called Additional Carbon Accountability that looks at this and kind of a fair allocation of carbon budgets, both historic and future. And the EU would have an additional carbon accountability probably of like 70 gigatons or something like that. If we need to address historic emissions, that's above our fair share to actually bring temperatures back to 1.5 degrees. And I would say that maybe it's not strictly necessary to have permanent carbon removal when you're dealing with historic emissions, because then you're not enabling continued fossil fuel use. You're just kind of abating previous harm. But it's really difficult to scale up forest carbon anyway. Like it's a few gigatons per year probably that we could do. So the volumes that we're talking about requires permanent carbon removal anyway. Because it's so limited what we can do with the more temporary ones.
Thanks. And now I will have some more questions to our presenters. Well, first off, to Cyril, there are a couple of questions on the kind of methodology and the issue of uncertainty, dealing with uncertainty when it comes to permanence or like the durability of carbon storage. And also about what are the reasons why the land-based removals are so impermanent. So if you could give a comment on that.
Yeah, sure. Thank you very much. Maybe before I pick up on one comment that Robert raised, I think for negative emissions, if you want to cool down the planet and maintaining it at that state, you also would need permanent removals for that, just from the concept of, because it's the same, a ton of CO2 that is emitted in the atmosphere continues to heat for millennia to come. So if you want to neutralize that, then you also need to remove it and make sure that it doesn't enter the atmosphere again. The uncertainties, of course, sort of when you think about, I think the uncertainties are there very much driven to policy making. Where do we make the cut, for instance? But when we look at sort of the methods that we have to remove CO2 from the atmosphere, actually the uncertainty within the ranges, I think, are ever so often not too much of an issue, because either they sort of are in the range of decades to centuries, then you have biochar, which is sort of mixed, or they are really, really, really long lasting. And I think whether it's 10,000 years, 100,000 years, a million years, that doesn't matter too much. We haven't dived into these long-lasting levels of permanency because it's just the models, the uncertainty within our climate modeling is then too high to address that. And the last bit was about the land-based carbon dioxide removal methods. And I mean, my take is sort of that what we found isn't necessarily linked to whether this has to be stored within geology or whether it can be land-based achieved. But if you look at the different methods of what their properties are, then ever so often temporary removals are more common amongst the land-based removal methods. That being said, personally, I think, for instance, afforestation can be durable, but you need to think about afforestation as sort of having a piece of land which would naturally, under historical and future climate, sustain forests. And then you have a forest and you make sure that this is being kept as a forest. Then you build up a carbon pool, and as long as this forest remains intact, then it's safe. If there is a wildfire, for instance, if sort of the forest would naturally occur, then it regrows. It even produces some biochar. So actually, over time, you actually even can store a little bit more carbon than you used to. But if you go ahead and just say a tree, look at the tree, then obviously as soon as you cut down the tree or make use of it as furniture or so, then the durability is smaller. The same somewhat holds true for soil carbon, but there the challenge is as soon as you stop maintaining it, typically, that you lose some of the content, or especially if you change your behavior and you start to mix the soils up again such that they can oxidize. So for me, it's not a question about sort of land-based and technological or whatever, but it's more due to the properties.
Thanks. Now I have a question that I think is from Felix and Josh about the impact of Cyril's research, or like the kind of the science that goes behind it, to your research on like policy recommendations, and how do you like deal with the issue of durability, the minimum durability of 1,000 years to consider something permanent, in like figuring out the framework for integrating CDR into policy mechanisms.
Sure. So I think it's super helpful to have something empirical, because at the time, we were trying to sketch out a framework that was purely conceptual, which was, if something isn't physically equivalent to a fossil emission, it can't be used to neutralize that, which instinctively makes a lot of sense, but we didn't have a number on it. So it's quite nice to then go and have a conversation with policymakers. We say, okay, here's an article published in a top journal which says, for the purposes of neutralizing a fossil emission, it has to store carbon for a number of years. I think just stepping back from all of this is, to some extent, this conversation about fungibility is only really relevant if you're talking about compliance market integration. You don't need to make these units and construct this framework that we sketch out if the end goal isn't to try and artificially create this fungibility in a compliance market. You only really need to do that step if that's your end goal, which the EU seems to be taking a slightly more conservative approach and only saying perhaps permanent CDR only. What we still don't know about the UK is whether they will go ahead and integrate woodland units, which then they will have to construct this sort of artificial fungibility and apply the various frameworks that measures in the framework that we've sketched out. So yeah, Cyril's paper is super helpful in that regard, because it kind of gives us validation of the ideas we were trying to present.
Right, and another quick question to Cyril. I was thinking about that as well. The issue of using CDR options with limited durability to compensate methane emissions, because I like, from the very limited understanding, methane stays in the atmosphere for a shorter period of time, but has a greater climatic impact. Have you been like, is there research on that part as well? You could give a comment.
Yeah, absolutely. Robert and we already talked about that also online once. And for this manuscript, we decided to skip that, to have like, because the discussion would be too big. And I personally like brief manuscripts in that sense. Now, I think when we think about methane, then we need to think about what do we actually want to achieve? Do we want to achieve sort of maintaining the same level of warming? Then certainly non-durable CDR can be useful, as well as permanent CDR. But then if you go ahead and if you think about limiting warming to a certain level, I think methane is super powerful because of its short lifetime to actually reduce peak warming. And as such, I think it's a more powerful tool to have it in mind than to just think about how can we offset it. That being said, there is also different metrics and models of how you convert that. And what we found out is sort of if you use GWP star or linear warming equivalent, and then balance that, the cumulative amount, now it gets a little bit technical, sorry for that, the cumulative amount of GWP star or linear warming equivalent with CDR. And also there, if you have temporary CDR, that you also calculated GWP star or the linear warming equivalent, and to have the cumulative amount. If the two are balancing in one another, then the temperature output is constant in that sense.
Okay, and Robert?
Yeah, I wrote about this before and proposed this very thing that you could use temporary storage to offset methane, but it's more like it was more a theoretical proposal and also giving an avenue for very temporary credits. But I think we have to talk about also, we don't really have room for it now, but net zero greenhouse gas emission targets are not the best. Like, you don't have to net out the methane. You need to do net zero CO2 to stop warming, and you need to reduce methane. There's no strict reason for asking people to compensate for ongoing residual methane emissions when you reduce them. That really just pushes the burden to reach net negative emissions to farmers, like rice farmers in Pakistan or something, instead of like historic emitters. So I think we should let go of net zero greenhouse gas targets and instead have net zero warming targets.
Felix, you were raising your hands if you want to comment on that.
Maybe Cyril first, if we still have time, because he wanted to talk directly.
Yeah, sure. Very briefly, there has also been papers on that, and I personally also very much support the concept of like-for-like balancing, meaning sort of when you do carbon dioxide removal, or if you have an emission, then you balance that with carbon dioxide removal that has a similar level of permanence in respect to how long the gas warms the atmosphere and where it comes from. So if you, for instance, have some sources from geology, fossil fuel emissions, then you would have carbon dioxide removal with storage in geology. If you have methane emissions, for instance, not natural gas, but biogas or so, manure or whatever, then you could also balance that by removals that are land-based in that sense.
Right, I'm afraid that we are running out of time. The discussion is very interesting, and I'm sorry that I did not manage to relay all of the questions that you have been asking. And but I would like to just a technical note: the presentations will be available. So somebody asked about that as well, yeah, it will be available on the record of this webinar will also be available on the CDR forum. So please do not hesitate to reach out for that. And to close the session, I would like to thank the panelists and the presenters for today's meeting. It was a very interesting discussion, and thank you also for all the participants. There has been at the highest point there was over 160 people. So thank you so much for taking the time and for listening to those presentations. And yeah, and in a month we see each other once again on another episode of our UPTAKE webinar series. Thanks so much, and have a nice rest of the day.